Okay, hi everybody. I'm Randy, KJ7WLT. So I'm going to go through some of the questions and answers from section T6 on the technician exam. There are a lot of questions in the section. I don't cover them all here, but I'm going to try to kind of focus on the ones where I hope I can give you a little insight maybe on what the question's about and why one answer is right, and a little bit about the physics behind some of these things, not too much. There's 4 different sections, and this shows a number of questions in the question pool in each section. But I think on the actual exam, there's only 1 question from each section. So a total of 4 questions from today's set of material. And it's all on the electronics and electrical components. The whole question pool you can find on the ARRL website. Some of the figures and material in these slides came from this AD7FO training material. Very useful. Personally, when I was studying for these exams, I liked the hamstudy.org website as a good way to get practice tests and to go through the questions and get hints on the right answer and things like that. Going through that many times over is, I found, the best way to learn the material and remember the answers. So I'll go through some things, and feel free to interrupt me if you have questions as we go along, and I'll try to pause now and then and see if there's any confusion or questions. But I'm going to go through some of the questions that I said, and I'm not going to go through them in exactly the order that they're in the book, because some of them fit together better if they're totally out of order from the way they're presented in the book. So I'm sort of trying to group them by common themes rather than going through them in order. So first of all, what electrical component opposes the flow of currents in a DC circuit, just direct current? It's opposing the flow of current, and so it's called a resistor. And you can remember that because to resist means the same thing as to oppose. And so when current is flowing through a wire, there's friction of the electrons moving through the wire as it goes, and so it slows down, and that's the resistance. Is everyone able to see and hear okay? Okay, let me know if there's any problems with the audio or visual. And this symbol down here at the bottom is the symbol for a resistor in a schematic diagram, which we'll also be talking about. So in diagrams that you see of how things are wired up, you'll see this symbol for a resistor. And I think somebody isn't muted. You might all want to mute. Vu, maybe you need to mute.
Okay.
So this question says, what type of component is used as an adjustable volume control? And it's actually related to the last question because it's a resistor, but it's a variable resistor because you can adjust the resistance. And as you adjust the resistance by changing where this wire is connected to this resistive element, you can change how much resistance the wire has. But in the question and in many contexts, it's not called a variable resistor, it's called a potentiometer. It's also sometimes called a variable resistor, but here it's called a potentiometer. It's something that has to be variable, though, since it's adjustable, so it's not a fixed resistor, but it's a potentiometer, and it sort of meters the amount of current that's flowing, and therefore the volume. So what electrical parameter is controlled by a potentiometer? Well, we just saw that on the last slide. A potentiometer is a variable resistor, so it's the resistance that's controlled by the potentiometer. Now, another common electrical component is a capacitor, and this is sort of the schematic diagram of a battery here connected to 2 wires with a capacitor in it. And if you didn't have anything in here, you would just have current flowing from one node of the battery to the other, with some resistance in the wire, maybe slowing it down. But this capacitor has a break in the middle that current can't flow across at all, but it has 2 metal plates that can accumulate charge. And so what happens when you connect it to a battery is the current starts flowing, but it charges up one side of the capacitor and removes electrons from the other side of the capacitor. So you end up with an electric voltage across this capacitor, and the current stops flowing when it reaches its capacity for storing electrons. So a capacitor has some capacity for storing electrons, which is one way to remember what it's called. And it's created by having two conductive surfaces that are separated by an insulator or a dielectric, as it's called in the figure at the top. So that's a capacitor. And then another very important component in radios is an inductor. So a capacitor can store energy in an electric field because it builds up a charge across the two plates of the capacitor. An inductor is something that can store energy in a magnetic field. So if you remember, electromagnetic waves are the sort of waves that we care about for radios. There's an electric field and a magnetic field that are both important in a propagating radio wave. And in a current going through a wire, there's an electric current that's going through the wire as electrons are flowing. But it turns out when a current flows through the wire, it creates a magnetic field in the vicinity of the wire. And if you wrap a bunch of coils of a wire around something, then you're basically increasing the magnitude of that electric field because the current is going parallel. In one loop of the wire, it's going parallel to the way it's going in each of the other loops. And so if you double the number of loops here, you sort of double the magnetic field that you generate for a given current that's flowing through it. So if you think about an electromagnet, like the big, huge electromagnets they use to pick up cars at a junkyard or something, those are created this way by wrapping coils of electrically conducting material in such a way that it creates a very strong magnetic field. Now, in the context of a radio, we're not making magnets that can pick up metal, but there's a weak magnetic field that's very important in the way a radio operates, and that's created by this inductor. So these are some pictures of actual inductors. And one reason it's very important is that the way a radio can tune into a particular frequency, when you hook it up to an antenna and you're trying to hear something on one frequency out of all the other frequencies of radio waves that are bouncing around and hitting your antenna, is that it uses a very special kind of circuit that's created by connecting a capacitor together with an inductor with a wire connecting them. And in this picture, there's no source of power, there's no battery, there's also no antenna connected. So if you just have this sort of closed system, then you might not think electricity would flow at all. But if we suppose that we start with a bunch of charge on one plate of this capacitor and less charge on the other plate, so that there's an electric field across here that's storing some energy as an electric field, and then you sort of let the current flow, then the charge is going to want to flow from the side that has more charge over to the side that has less charge. Whoops. And as it flows, if there weren't an inductor here, if this were just wire connecting the two sides, it would flow and it would slow down, and eventually you'd reach a sort of steady state where the charge is just equally distributed around the whole loop. But what happens when you put this inductor here is that as the current starts flowing, as it goes through the inductor, it induces a magnetic field that stores some of the energy as a magnetic field. And as the current all accumulates over here, it then starts flowing back the other way, and it flows back and forth and back and forth. And the idea is very similar. It's a little harder to understand, but it's very similar to what happens with a pendulum. If you are familiar with a pendulum, like a swing that you might push in the playground, if you pull it up to its sort of maximum height before you release it, it's not moving at all. It doesn't have any kinetic energy, which is the energy of movement. Instead, it has what's called potential energy because it has the potential to start moving due to the fact that gravity is trying to pull the swing down and you're holding it up. So there's some potential energy. And when you let go of it, it starts to swing down. And when it gets to the bottom, then all of that potential energy has been converted into kinetic energy. It's moving as fast as it's going to go. There's no more potential energy, at least if we don't break the string here, it can't go down any further, but it keeps moving because it has all of its energy and the kinetic energy, and it keeps going and rises up to the other side until it gets high enough that all of its kinetic energy has been converted back into potential energy. And then it starts falling in the other direction. And again, it's all kinetic energy at the bottom, goes back up to the other side where it's all been converted back to potential energy. So that's sort of how a pendulum works. And it's converting energy between potential and kinetic. And a tuned circuit that's used in radios is similar, but it's converting energy between electric fields and magnetic fields. So another thing we know from pendulums is that the frequency with which the pendulum goes back and forth, or the period, the time it takes to go back and forth, depend on the length. If you make it shorter, it oscillates more quickly. If you make it longer, it goes more slowly. And so you can adjust, if you could adjust the length of the rope here, you can adjust how fast it goes back and forth. Another thing we know about pushing a swing at a play yard is that you have to keep pushing it if you want it to keep going. And the reason is that even though in principle, all the energy stays in the system and just goes back and forth between kinetic and potential, in reality, there's also friction at the top of the swing. There's air resistance of whoever's sitting in the swing moving through the air, and that's removing some energy from the system. So if you want to keep it moving, you have to keep putting new energy in by pushing the swing now and then. And if you want to push it efficiently, you have to push at just the right times. You have to push when it's in the right position, that you're pushing at the same frequency that it wants to be swinging at. If you try to push at a totally different frequency, you'll find it doesn't work at all well. So you can make it swing higher and higher if you keep pushing at the right frequency. And in physics, that's often called a resonance, that the frequency at which you're forcing it or pushing it in this case agrees with the natural frequency that it wants to oscillate at. And if you do that, then a little bit of energy being put in the form of pushing it can make it go higher and higher and higher, because you're sort of complementing the natural frequency that it wants to oscillate at. Okay. So what does that have to do with radios and antennas? Well, as I said, this sort of LC circuit, or inductor capacitor circuit, as it's often called, works in the same way, but it's transferring energy between an electric field and a magnetic field. So if all the charge is on one side of the capacitor and we let it start flowing, as it flows through the wire, as it goes through the inductor, it induces a magnetic field. And so you can think of this as the electric energy is being converted into magnetic energy. At the time when all of the current sort of is flowing and we have no potential difference across the capacitor, so there's no more electric energy being stored, then there's a lot of, or all of the energy is now being stored as the magnetic field in the inductor. And that magnetic field induces a current that sort of keeps the current flowing for a while, even after it's gotten to this state where there's the same voltage on both sides of the capacitor. So the current keeps flowing because of the current that's being induced by this inductor. And what happens is that all that current, all that charges now accumulate on the other side of the capacitor. So this is like the pendulum has gone all the way up to the other side. And then it just repeats, it goes back the other direction. Again, it gets converted into magnetic energy, like the pendulum being at the bottom, and it's all kinetic energy. And then it goes back the other side and gets back to exactly where we started. And in an ideal world, that could keep going forever. But just like in a swing, there's resistance. Some energy is being taken out of the system by the resistance of the electrical wire. And so if you want it to keep oscillating forever, you have to keep putting a little bit of energy in. And how much or what frequency you want to put energy in at, just like in the pendulum, it depends on what's the natural frequency at which this oscillates. And like in the pendulum, you can adjust that by changing the length of the swing. For the tuned circuit, you can adjust the frequency that it wants to oscillate at by changing the inductance, changing the number of coils here, for example, or changing the capacitor. Or you can make a variable inductor by having the wire here with an adjustable thing that comes down to some location along the side of these coils. So as you turn the knob on your tuner on your radio, what you're doing is basically adjusting the amount of inductance the inductor has, and that changes the frequency at which this wants to oscillate. And now if you hook it up to an antenna, the antenna is giving some energy input, a very small amount of energy, but as electrons move back and forth in the antenna that were set in motion by the electromagnetic waves, the radio waves propagating past the antenna, there's radio waves propagating past the antenna at lots of different frequencies, all sorts of radio sources that are hitting your antenna. But when it starts forcing this electrical circuit, only one of those frequencies is going to be at the right frequency to amplify the signal in this oscillator. And so depending on how you have it tuned, you will pick up one signal out of all those radio waves that are hitting your antenna. You'll pick up one particular frequency that will get amplified significantly as this goes back and forth because it will be resonant at that particular frequency. So that's kind of a lot of physics, but that's the basic idea of how a radio receiver works and how you can tune a receiver to pick out one frequency out of all the radio waves that are constantly hitting your antenna. And yeah, so this impedance, along with the resistance in the wire, makes the amplitude decay in time. But if we force it at a particular frequency based on what the impedance and capacitance are, even a very small forcing from a weak signal on an antenna can be amplified greatly by this sort of circuit. And that's how you tune your radio. Okay, that was a lot. So let me stop there and see if there are questions about that, or give you a minute to absorb that before we go back to looking at the questions that are related to this. Any questions? Yeah, so the reason I wanted to say a bit about this is because I think some of the other questions will be easier to remember what the right answer is if you at least have some idea of what's going on in this sort of circuit. So the fact that you have an inductor, which is this coil of wire, and you want to be able to vary the inductance. So you need a variable inductor, and you need a capacitor, and you need an antenna in order to make a radio receiver. Okay, so there's a bunch of questions that are kind of related to what we just looked at. So one of them is, which of the following is a resonant or tuned circuit? Resonant circuit or tuned circuit means the same thing. It means you can tune it to resonate or to oscillate at one particular frequency. So which is the right answer here? Take a look at these. We just saw it in the figure on the previous slide. You can make a tuned circuit by putting an inductor and a capacitor together. And so here's the schematic diagram of what we were just looking at. The capacitor is indicated this way, and the inductor is like a coil of wire. And remember that the inductor stores energy in the magnetic field, while the capacitor stores energy in the electric field, and this oscillating or tuned circuit that's going back and forth between the two. So what electrical component stores energy in the electric field? We just saw that. That's the capacitor, right? It has some capacity to store electric energy. And what type of an electrical component consists of conductive surfaces separated by an insulator? Well, that's the capacitor. It's two plates with the wires coming in, but current can't flow across it, so it builds up in the electric field. And then the other component, what type of electrical component stores energy in a magnetic field? That's the inductor. And remember that the current going through the wire is inducing a magnetic field as it flows. And so that's why it's called an inductor. And if you coil up a bunch of wire, what sort of electrical component do you get? An inductor. This is a variant of one of the previous questions. Which of the following is combined with an inductor to make a resonant circuit? Remember, there's two basic components, the inductor and the capacitor. Okay, so those are all of the questions really that relate to these resonant circuits and the capacitors, conductors, inductors, resistors. So are there any questions about any of that material before we go on? Okay, so the next section of material is about semiconductors. So a conductor is something that conducts electrical currents. Electrons can flow through it easily. It may have some resistance, but things flow through it pretty well. An insulator doesn't allow electric current to flow through it at all. But then there's things that are kind of in between that are called semiconductors. And I'm sure you know the term semiconductor because they're the basic things that go into integrated circuits and transistors and all those sorts of things. In particular, for the technician class exam, the only kind of semiconductors you need to worry about are transistors and diodes, which we'll talk about in a minute. So if you just remember semiconductor equals transistor or diode, then this question, which of the following components consist of three regions of semiconductor material? Since it is made out of semiconductors, there's only one of these possible answers that's a transistor or a diode, namely a transistor. So a transistor, it has a symbol in a schematic diagram that looks like one of these things at the bottom, often with different sort of things in the circle, but typically there's like three connections on a transistor because you have current that can go in one end and out the other, but then there can be another current coming in the side that sort of controls how conductive it is and can be used to do all sorts of things with a transistor. So there's three inputs typically to a transistor, or maybe two inputs and one output. But anyway, there's three wires coming in, and that's usually a circle of some kind that's used to denote it in a schematic diagram. So here's one application of a transistor. But it's related to this question. What is a term that describes a device's ability to amplify a signal? So to make it larger as it propagates. Well, out of these, it wouldn't be resistance because that's sort of decreasing things. So that gets rid of a couple of these. The answer is gain. And just remember that gain sort of means increase, and it's increasing or amplifying a signal is gain. So I think I've given this away already, but which of the following can provide power gain? Well, out of these, what we've just been talking about is the transistor. Which of these components can be used as an electronic switch? Well, this is another application of a transistor. You can use it to switch whether current is going one way or another. Then there's a couple of things that you just kind of have to memorize, I think. What are the names of the electrodes of a bipolar junction transistor? This is just one particular kind of transistor that has three connectors that are called the emitter, the base, and the collector in this case. And the symbol for this kind of transistor in a schematic diagram is the circle, again, with three lines coming in, and with this an arrow going in or out of one of the internal line. But mostly you just have to remember that anything that looks sort of like this is probably going to be a transistor in a schematic diagram. And for this particular bipolar junction transistor, you just have to remember that it's emitter, base, and collector. Okay, what does the abbreviation FET stand for? So a hint, we've just been talking about transistors, and this is another kind of transistor. So two of these answers you can throw out altogether. It's either a fast electron transistor or a field effect transistor. And to remember which one it is, it's actually a field effect transistor. Remember also that we've been talking about the electric fields as storing energy, for example. So it makes sense that F might stand for field in this kind of transistor. So it's a field effect transistor. And it has a slightly different looking symbol, but again, it's a circle with three lines coming into it. So if you remember a couple slides ago, what kind of transistor has a gate, a drain, and a source? That's not the one we just looked at, but the one, oh, it is the one we just looked at. Sorry. I thought it was, oh, that was, sorry. I see, I'm getting confused. The bipolar junction transistor has an emitter, a base, and a collector. The field effect transistor has the gate, the drain, and the source. So you just have to memorize what terms are used for which transistors for a couple of these questions. The one with a gate, a drain, and a source is the field effect transistor. Okay, before we move on, are there any questions at this point? Go back and review. So we have a field effect transistor, a couple of questions on that. We had the bipolar junction transistor with the emitter, base, and collector. A transistor can be used as an electronic switch. It can also be used to provide power gain. And gain is the device's ability to amplify a signal. And all of these transistors are built up of these semiconductor materials, and they can allow varying amount of current through, and there's often a third wire that comes in that sort of helps control how much current is going through. So they often have 3 connections, and their schematic diagrams are always a circle with 3 lines. Okay. So I said there were only 2 kinds of semiconductors you really have to think about for this exam. One is a transistor, and this is the other one. What electronic component allows current to flow in only one direction? So normally if you hook a wire up to a battery, the current might flow either direction, depending on which end you hook up to the positive and which to the negative. But the wire itself would allow current to flow in either direction. But there's electronic devices that can keep it from flowing in one direction and allow it only to flow in the other direction, like a one-way street. And this is the other kind of semiconductor. It's not a transistor, it's a diode. And so the schematic symbol for a diode is this little triangle that's in the wire and that's pointing in one direction. It's like a one-way arrow sign that shows which way the current is able to flow in a diode, and it would impede current from flowing at all in the opposite direction. So very important if you're in a situation where you need to make sure current is going in one direction. This one, you just kind of have to remember what's true about forward voltage drop in a diode. The answer is it's lower in some diode types than others. No good answer, no good way to remember that, except maybe to remember that there's lots of different types of diodes. So some of them it's lower, some of them it's higher. So this turns out to be the right answer. Okay, now this moves on to a slightly different topic. What's the function of an SPDT switch? So again, you have to kind of remember what that means. It turns out it stands for a single pole double throw switch. So what does that mean? It means you have a wire that's coming in and a switch here that can connect it either to the wire on top or to the wire on the bottom, depending on which way you switch it. So it's got a single pole because there's only one little connector here in the middle that you can switch one way or the other, and a double throw because you can throw it one direction or you can throw it the other direction and make the current flow through the top wire or through the bottom wire. So it's a single pole double throw. So if you remember that SPDT stands for something like single pole double throw, then it makes sense that it's a single circuit that can be switched between one or of 2 other circuits. But you just kind of have to memorize that, or at least remember what that acronym stands for, so that that answer makes sense. Okay, so what's the name of an electrical wiring diagram that uses these standard component symbols? I've talked about what some of these symbols are. This is the symbol for an inductor. This is the symbol for a capacitor on the right. And then there's some wires connecting them. And I've used the term. What's the term that we use for this kind of diagram that sort of shows what components are hooked up and how they're hooked up? called a schematic diagram. It sort of shows the scheme of how things are connected. And I've mentioned what the symbols in a schematic diagram are for various things. So we have a resistor up here in the top left, but then there's various kinds of resistors. There's an adjustable or variable resistor, also called a potentiometer. Remember that you can use to adjust the volume, for example. And that looks like a resistor, but this arrow here indicates something that you can slide along it and change how much resistance it's supplying to the wire that's going through it. So it's a variable resistor or a potential. Well, here's another one that says it's the potentiometer. So I guess it depends sort of on the context. I think they're both variable resistors, but a potentiometer is the term that's used if it's sort of something that's a volume control, for example, whereas a variable resistor could be used in other contexts as well. Capacitors, this is the main one that we've seen. I think the only one you have to worry about for this exam. Inductors, remember that it looks like a coil of wire going around something, and so this little schematic diagram shows a coil. You can have a variable inductor, just like a variable resistor. So again, it has an arrow sort of going across that indicates you can adjust how much inductance it has, which, as I mentioned, is very important in tuned circuits. If you want to tune your radio to a particular frequency, you need a variable inductor to do that. Also, one of the questions involves a transformer, which looks like an inductor separated from another inductor. So the idea of a transformer is that it can transform power from one voltage to another. And the way it does that is that the current flowing through one wire induces a magnetic field, which induces an electric current in the other wire. But if you have different numbers of coils on the two sides, then the current that's being induced in one wire has a different voltage than the current that's driving it in the other wire. And so it can transform one voltage to another, for example. Then there's diodes. We've seen this sort of one-way travel symbol for a diode showing that current can only go in one direction. There's a few other types of diodes. In particular, the one on top here is an LED, a light-emitting diode, like the LEDs in light bulbs or your headlights of your car, maybe, or a flashlight. It's a diode that has made up of special material that emits light as the current goes through it. It's again a kind of semiconductor. And then there's various kinds of transistors that are all these circles with three lines coming in. These sort of switches, an antenna, a lamp, batteries, grounds, wiring systems. I think this picture came right out of the technician class license book, but you can find lots of other figures on the web that have huge number of different specialized components. So it's good to be familiar with the basic ones because there are several questions that show you a schematic diagram and then ask you to identify various components in it. So from what we just went through, well, first of all, which of the following is accurately represented in a schematic like what's over here on the right? The wire length, the physical appearance of the components, the component connections, or all of these? Well, it's not really showing the physical appearance of the components. That would mean it would be like a picture of what a antenna or a variable capacitor actually looks like, but they're not. They're these sort of schematic symbols. So it's not the physical appearance. Also, the wire lengths, the distance between things, isn't necessarily to scale in these schematic diagrams. Things are just placed so that you can see everything clearly and you can see how they're connected together. So what is really important is how they're connected together. So the component connections are what you're really able to see in a schematic diagram. And that's the only thing that the schematic diagram, at least from this list, tries to show you is what the components are and how they're connected. So here's one of the questions that asks you to identify some components. So I'll give you a minute to think about these. What are components 1, 2, 3, and 4? First of all, what's component 1? The wire goes through the zigzag. That's a resistor, right? As the current goes through there, it's resisting the flow. That's what the zigzag is supposed to indicate. How about component 2? It's a circle with 3 lines coming into it. We've seen several of those. That's the transistor. Component 3, didn't really talk about, although it was on the previous page of symbols. It looks kind of like a light bulb. That's just a lamp or a bulb of some sort. And then figure 4, you might have seen that on the table too. That's a battery. And component 5 isn't one of the questions, but that's a ground, where the battery, say, is grounded. This is the same figure as before, but a different question. What's the function of component 2? So what is component 2? Well, it's one of these circles with 3 lines. It's a transistor. So we know various things a transistor can do. Which of these things is something that a transistor can do? One thing a transistor can do is control the amount of current that's going through it. And that's the only one of the things that are listed here that a transistor does. Here's another schematic diagram. So I'll give you a minute to think about this. Component 3 and component 4, what are those? Component 3, it's this curled up piece of wire. That's an inductor, but the connection can be at a variable point along the edge of it here. So it's a variable conductor, or inductor, sorry, not conductor, inductor, variable inductor. And how about component 4? It's this thing that kind of looks like an antenna sticking up in the air here, and that's an antenna. Oh boy, here's another schematic diagram. Getting a little more complicated here, but I think we've seen most of these already. So components 8, 9, 4, and 3 are the ones that are asked about on various questions. So I'll give you a minute to think about those components in particular: 8, 9, 4, and 3. So component 8, it looks like this one-way travel sign. That's the diode, but it's emitting something. So it's a light emitting diode. How about component 9? The zigzag line, which is a resistor, but then you can vary the amount of resistance it's giving by turning this dial and moving this little arrow along it. And so it's a variable resistor. And then component 4 over here. This is a case where we have, this is a plug here, so it's plugged in here and there's power flowing through this circuit. But then there's another circuit over here that's sort of detached from it, but there are these 2 inductors. And remember, as the current goes through here, it induces a magnetic field that induces a current over here, but possibly at a different voltage. And so we end up with a transformer. And finally, component 3 is the only other one they ask about in this figure. Well, this looks like a little switch that you can either open or close that turns this power supply on or off over here. So that's called a single pole, single throw switch. We saw before a single pole double throw switch where there was only one little pole coming out, but it could connect to 2 different wires. But this is a pole that can connect only to 1 wire or else be open, disconnected when the circuit is turned off. So it's a single pole, single throw switch. Okay, before we go on, let's see, are there questions at all about schematic diagrams or what any of these symbols mean or what any of these different types of components can do? Maybe I'll go back to this. Now that we've seen a bunch of schematic diagrams, go back for a minute to this figure, which shows all of, or not all, but a small subset of all the different symbols that could be used in schematic diagrams. But this is already more than what you need to know for the exam, but it's good to look at this sort of thing and try to remember what these different classes of symbols mean. The zigzag for resistors, the coils for inductors, the circles with 3 lines for transistors, the one-way diodes, and capacitors, like a wire with a gap in it. Okay. So now suppose we have a device that combines several semiconductors into a single package. Which of these words or phrases would describe a small package that contains lots of semiconductors? These days, it might contain millions of semiconductors. It's an integrated circuit, IC. It's the basic building block of radios, as well as most other electronic things, are integrated circuits. It just means it's a bunch of different semiconductors that are all integrated together into a single, very small, often package. We've already talked about this a bit. What component can change 120 volt AC power to a lower AC voltage for other uses? Well, we're transforming one voltage to another voltage. It's a transformer. How about if we have an alternating current? So if you plug something into the wall at 110 volts, that's alternating current. The current is not just flowing straight from one end of a battery through a wire to the other end. That would be a direct current. But when you plug something into the wall, it's an alternating current, and the electrons are forced back and forth very rapidly, about 60 times per second, or 60 hertz typically is the frequency with which electrons go back and forth in the wire when you plug something into alternating current in your house. But then if you want to plug your 12 volt radio into that in order to power your radio, you not only have to convert 110 volts into 12 volts, you also have to convert that alternating current into direct current that's only flowing in one direction along a wire. So if you want to take an alternating current and turn it into sort of a one-way current, then there's a particular electrical component we've talked about that only allows current to flow in one direction. And so that's kind of a building block often of this sort of device that can turn an alternating current into a one-way current, because it can just let the current go in one direction and block the current when it's flowing in the other direction. So that's called a diode, but that's not on the list here. So the answer they're actually looking for here is what's called a rectifier. And a rectifier might be built out of one or more diodes, but the name of the device is often called a rectifier. And the word rectify means to set right or to straighten out or to purify. And so remember that a rectifier is taking this alternating back and forth current and forcing it to go only in one direction. And so it's setting it straight, so to speak, and it's rectifying it. It's a rectifier. And it might be built out of diodes. Okay, you're probably familiar with this from your house or your car. What electrical component is used to protect other circuit components from current overloads? Well, in your house, you probably have a circuit breaker these days, but once upon a time, houses had fuses. Your car probably has fuses. Your radio has fuse, probably. And so it's just a device that's designed to only handle a certain current and then burn out. The wire just vaporizes if the current gets too high, so that rather than that high current going into your radio and frying expensive electrical components in your radio, instead it just burns out a cheap little fuse that you can replace after you've fixed whatever was wrong. All right, and then there's several questions about different types of batteries. Again, you could just memorize this, but I'll give you some hints to help you remember the answers. Which of the following battery chemistries is rechargeable? So there's lots of different kinds of batteries. There's, for example, lead acid batteries are the ones that are in cars typically. Lithium ion batteries are the ones that are in cell phones and laptops and radios and various other things. Nickel metal hydride batteries are like often the A or C cells that you buy. So which of these is rechargeable? Well, the answer is that all of these are, and it's pretty easy to remember because we know that the battery in your car is rechargeable. Every time you run the car, you're recharging the battery automatically. Otherwise, you'd have to keep replacing the battery in your car. We know our cell phones and laptops are rechargeable. So even if you don't remember what nickel metal hydride batteries are, the fact that both B and C are rechargeable means all these choices must be correct. And then there's another related question. Which of the following battery chemistries is not rechargeable? So some of these answers are right from the previous slide. So we know they are rechargeable, like lithium ion and lead acid. So those can't be the answers. The other two we haven't seen, but the previous slide, there was nickel metal hydride. And nickel cadmium is one sort of battery of that type, also involves nickel and some other metal. And so that's also rechargeable. So the one that's not rechargeable is the only one left, the carbon zinc. And I guess that's all the slides I had. So we got through that pretty quickly, but there was a lot of material there. So I'm happy to go back. Maybe we should review these last few slides again. Where did we start here? So remember, when you put lots of electrical components in a small package, you get an integrated circuit. What computers and radios and most electronics are built out of these days. If you're transforming power from one voltage to another, it's a transformer. If you want to change alternating current into current that's only going in one direction, you have to rectify it with a rectifier that might be built out of diodes. And then a fuse protects the circuit from overloading. And the rechargeable batteries, all of these are rechargeable. And on the next list, the only one that's not rechargeable is the carbon zinc. So are there questions about any of these topics at this point? Do you want me to go back and review any sections of this?